Hey everybody, today I'm presenting our work titled Beware of the Simulated DAG, Causal Discovery Benchmarks May Be Easy to Gain. This is joint work with Christoph Seiler and Sebastian Weichwald, and I'm Alexander Reisach. Long story short, we're arguing that in additive noise models, variance tends to increase along the causal order. And therefore, just by sorting by variance, we can achieve state-of-the-art result on common benchmarks. And this may be problematic because it's not clear whether that performance really translates from the benchmarks to real-world data. Now, let's first jump into additive noise models. So they typically consist of a set of variables that are defined as sort of transformations of other variables and an additive noise term. And combined, they form a causal graphical model. And the structure of that causal graphical model can also be expressed in binary adjacency matrix. And what that causal graphical model allows us to do is it gives us a factorization of the joint likelihood of the variables such that the value of each variable is given just by knowing the parent variables in the causal graph. And it's given according to the structural equations of the model. And now what our task in causal structural learning is to infer the adjacency matrix, the causal structure from observations of the variables. And there are a multitude of algorithms that have been developed for this purpose. And broadly speaking, they can be classified into two distinct classes. The first one is constraint-based, and constraint-based methods leverage conditional independencies to infer the causal structure, whereas score-based methods try to find a structure that maximizes some goodness of fit score, for example, the joint likelihood of the observations. And so in the real world, it's kind of hard to sort of find an unambiguous ground truth causal data set. So therefore, what often happens is people train and evaluate these models on synthetic data. And to come up with synthetic data, one needs to sample a graph, for example, a scale-free graph with a certain average degree, and they also need to decide a noise type and parameters and define the functional relationships or class of functional relationships between the variables. And then ultimately, to assess the performance of a structural learning algorithm, we can use different performance measures, and two notable ones are the structural intervention distance, which roughly speaking gives us an idea of how many interventions we would predict wrongly using sort of a given graph as compared to the ground truth graph. And there's also structural Hamming distance between the inferred graph and the real graph. What we can see on the right here is the structural intervention distance when trying to learn the underlying graph that characterizes the data generating process. When the graph has 50 nodes, the additive noise is Gaussian and the functional relationships are linear. What we see on the y-axis are different algorithms, and over sort of 10 repetitions, we can see that there are certain algorithms that give us something that sort of is fairly close to the ground truth, at least much closer than some of the other algorithms. So maybe one thing that's notable here is the sort of reddish algorithms here. They're based on continuous optimization. So this is one very recent development, and causal structural is a very active field of research with many algorithms being developed, especially sort of this type very recently. All right, and now what's interesting is to have a closer look at this synthetic data generating process, because it's kind of crucial to the evaluation of algorithms. Now, what we're looking at is sort of just a causal chain. And you can think of this as sort of one part of a broader, more complex causal graph that consists of many such interlinked chains. And what we're finding is that if we look at the position in the causal order, so for example, A would be position 1, B is position 2, C is position 3, and so on, then this position in the causal order is very indicative of the average marginal variance. So if you sample sort of observations and you do this for like many different graphs, then it tends to be the case that the further you go in the causal order, the higher the marginal variances of the nodes. And so this is linear data now with sort of certain edge weight ranges and additive noises. And what we see is that for a range of different data generating processes, this effect takes place regardless of the parameterization. So it may be stronger for certain parameters than for others, but we see it pretty much every time. And what we do now is we propose a measure that we term Varsortability. And Varsortability is the fraction of all cause-effect paths where the effect has a higher variance than the cause. So in this example of A, B, and C, we can see that there's 4 total paths in the graph, and in 3 out of the 4, so all except for the red one, the path is leading from a low variance to a higher variance node. And so we have a Varsortability of 3/4. So 1 would be the maximum and 0 is the minimum. And when we look at data generating processes, and we just, for different choices, we generate data and we assess Varsortability within them, what we see is that for linear functional relationships, also for nonlinear relationships, different graphs, different noises, we see extremely high Varsortability. So these are choices that are somewhat representative of what is usual in the literature. Depends a bit. You can get lower Varsortabilities, yes, but it tends to be quite high for common choices. And in the linear case, almost close to 1. So, and in the nonlinear case, on average, still greater than 0.7. So that would mean 70% of the paths within the sample graphs are leading from a low variance to a high variance node. Now, what's the effect of Varsortability on algorithm performance? What we can see here is a similar plot to before, except that now we see in orange box plots the raw data and in green the standardized data. We standardize because Varsortability is all about the variance. So if we standardize data, then the variance of all nodes will be equal. And what we find is that some of the algorithms that previously performed very well now perform extremely poorly once the data is standardized. And interestingly, this is the same as a method that we propose as a diagnostic tool, which we term sort and regress. Sort and regress does nothing except order, does 2 very simple steps. And first, order the variables by increasing variance. And then second, regress each node onto all of its predecessors in that order. And what we find is that this sort of very simple algorithm exhibits performance that is remarkably similar to some of the other algorithms here, be they combinatorial or continuous. All right, so why could this be the case? So the intuition here is that what the algorithms that are affected have in common is they rely in one way or the other on the mean squared error or something very similar to it. And the idea here is that if we want to explain away variance and we want to fit a directed acyclic graph, which is sort of what these causal models always tend to do, then we can only place certain edges, and there's usually a penalty and on how many edges we can place and the weight of these edges. And so if we put in an edge from a low variance node to a high variance node, then that edge can explain away a good chunk of the variance. And once the constraints come in, such as acyclicity constraints or penalties, then they tend to remove sort of the edges that cannot explain a lot of the variance. And these are the ones that are leading from low variance to high variance nodes are the ones that remain. And under high Varsortability, they tend to correspond to the true causal edges. So this is how mean squared error-based methods can, in effect, exploit Varsortability. And Varsortability has huge consequences on the identifiability of the causal graph from data, because Varsortability can reveal the causal order. So if Varsortability is 1, then ordering by marginal variance is a causal ordering. And the closer to 1 it is, the Varsortability is, the closer we get to a causal order. And the reason why we see Varsortability is because we commonly sample graph parameters IID, and this IID sampling means that regardless of where we are in the graph, we sort of sample according to the same rules. So everything that's happening is that we add additive noise in the additive noise models at each step along the causal order. And other than that, in expectation, we were doing sort of the same thing in terms of noise parameters and weight parameters. And so with this compounding additive noise, and depending on the parameters that we pick, we can drive varsortability. Now, we've seen the consequences in performance. So some of the mean squared error-based methods perform very well. And so this is regardless of the optimization, at least for the ones we've tried. But their performance drops markedly upon standardization. And the same is true for sort and regress. Now, on the right, I have another 3-variable chain just for illustration with a covariance matrix here that we can see in the bottom left here of that illustration. And what we see is that along the main diagonal, the variances of the nodes increase. Once we standardize, these variances are all 1. Now, there's a second pattern here, and that is not on the main diagonal, but on the first diagonal. And here we can also see an increase. Now, interestingly, upon standardization, we can still see that pattern. So that means the additive noise assumption may be a bit stronger than was previously thought, because the patterns that are being left are in fact quite remarkable and may allow to sort of, even in the standardized case, at least to some degree, still infer the causal graph by using a simple method that is not too different from sort and regress. All right, so what's the takeaway? In short, beware of the simulated DAG. So in benchmarking, it's important that data scale really matters. So what that means is whether or not the data is standardized can make, depending on the algorithm, a big difference. And also for real world data, it may not always be straightforward what's the right scale of measurement. So meters, millimeters, things like that. And depending on the algorithm, that can make a big difference. Second, we've seen that varsortability arises easily in synthetic data. Now, the question is, does that also happen in real-world data? So if varsortability is real, then some of these algorithms can achieve great results also in the real world, and sort and regress could in fact too. But if that benchmark performance does not translate, then maybe we should sort of not trust our simulated DAGs too much, or perhaps think exactly about how we want to simulate that data. And best practices that we recommend are at least to report varsortability in sort and regress, because that has, as we show, a big impact on the causal discovery performance of certain algorithms. And when it comes to simulating DAGs, it may be helpful to try and simulate real-world processes. So this would be a step away from just simulating some DAG towards simulating a DAG that really captures what is going on in a certain real-world process. So that way we can be sure we're not just gaming the benchmark, but we're really doing something that is applicable to the real world. And the ideal scenario would, of course, be to just use real-world data, because then there's no gaming the benchmark anymore. And so we've done a first test. This is what you can see on the bottom right. Just without going into too many details, what we see here in red is the empty graph line. So still, while some of the algorithms are a tad better than others, overall, the performance isn't great. So this could be an indication that varsortability may not be real, because some of these performances don't appear to translate to this real-world data set. But to really settle that question, much more further research is needed. All right. Thanks a lot for your attention, and goodbye.